All right. Chapter 2 is up next. We've worked our way through Chapter 1, which is all the different geometry things. Chapter 2 is a little bit shorter, and it's all about variation. Variation to us is going to mean sort of a way of describing the relationship between two different variables, or I guess the potential relationship between two different variables. We'll be looking, for the most part, we're sort of going to break it down into two categories. We're either going to have what we call a direct variation, which is where the two variables are linked. So that is, if you sort of increase one variable, you're going to increase the other, or sort of vice versa. If you decrease one, you're going to decrease the other. The other idea would be sort of then a complementary idea where you have two variables and values that are sort of moving out of sync. That is, if you sort of increase one variable, it actually drops the other one. That's going to be what we call inverse variation. So we're going to talk about inverse variation in skill number 8. In this video, we're going to talk about direct variation. So this is skill number 7. We're also going to talk about joint variation, which is sort of an extension of direct variation. That will be sort of one of our videos as well. But direct variation kind of lays the foundation here. So direct variation, I'm not necessarily explaining this exactly as it is here in the book. But direct variation is where you have two variables and the behavior is linked. The behavior is in sync. So, meaning if you increase one, it's going to increase the other, or if you decrease one, you're going to decrease the other, right? So they're values that are sort of linked together. You could think of some of our geometry situations, and so if you think of like the area of a rectangle, so what's going to happen to the area if you increase the length? Well, as the length goes up, assuming you kind of keep the width fixed at a certain value, the longer the rectangle, well then just the bigger the area is that you're going to have, right? So there's a direct relationship between those two values. The bigger, the sort of wider the length, the bigger the overall area. You can also think of this, the example here in the book is talking about the idea of sort of a driving belt on a pulley, right? So that is a belt that sort of is going over, what would maybe be a gear or something, or a pulley. So if you have something here and you have a belt that's going around it, right? So if this is sort of rotating and it's driving something else on the other side, obviously the bigger that sort of gear or that pulley is, the bigger the radius is. In that situation, the longer the belt that you need, right? The belt has to go around that pulley. So the bigger the radius is, the sort of longer the belt needs to be. So there's a relationship that is in sync. Those two values sort of move in the same direction. A couple other examples, we'll sort of be doing a few from the book, or just sort of in general. One example would be sort of braking force, right? So if you think of braking force, how hard you press the brake pedal versus how hard the brakes themselves actually clamp down onto the wheel, or the rim. You guys probably could tell me what the brake actually clamps onto. It's probably not directly the wheel. In any event, so the harder you press the pedal, right, the harder the brakes will sort of clamp onto the wheel, right? So braking force at the pedal versus braking force at the wheel, there's a direct relationship there, right? As you sort of increase one, if you press down harder with your foot, you're going to get more braking force at the wheel. Another sort of geometry kind of one, right? Sort of looking back at the different formulas we had in the last section, right? So the bore of a cylinder versus the overall cylinder volume. Again, sort of assuming that you are keeping what would be the height or the stroke of the cylinder like fixed. If you make a wider cylinder, if you increase the bore, you're going to get a bigger volume and sort of thus a bigger displacement, right? So in some sense, engine size generically versus what would be the bore of the cylinder. Or you could sort of keep the bore the same and make it deeper, make a bigger stroke. So stroke and then the cylinder volume, and thus the engine size would sort of also be linked. If you want to think extremely generically, a couple bad jokes, the amount of Wheaties you eat versus your athletic ability, right? So the more Wheaties you eat, as I understand it, then the more your athletic ability will go up. More Wheaties equals more athletic ability. Less Wheaties, less sports skills. So definitely eat your Wheaties if you need to be good at sports. And of course, that classic money versus problems, right? As I understand it, the more money you get, the more problems you have, right? More money, more problems, I believe is, I think it was Aristotle that said that. So that one goes way back. But it's that same kind of direct relationship, right? The more that you have of one thing, the more you have of something else. So these two things are linked. That's the concept. You guys are probably sick of hearing me talk about the concept. You probably want to just know, how do I actually solve one of these problems? So what does this relationship mean to me? There's two different techniques we can use. My sort of personal preference is this first one. We can actually use proportions to solve these. So use proportions to solve a direct variation. So the idea here, let's sort of just look at an example, obviously, to help us sort of set it up. So a 4-cylinder engine produces 100 horsepower, assuming that horsepower varies directly with the number of cylinders. So that is, right, sort of our engine power is going to be related to the number of cylinders in the engine. If I go from a V4 to a V6, I'm going to sort of increase the power. If I go from there to a V8, I'm going to increase it again, right? What would the power be for a 10-cylinder engine? So if I have this sort of baseline value, right, 4 cylinders gets me 100 horsepower, what would I get for a 10-cylinder engine? Sounds like a pretty big engine. So the setup here is to use a proportion, and what you want to do, excuse me, you can set them up a couple different ways. The key thing is you need to make sure that you're in sync. So in this case, the way it's set up is it's, right, so horsepower 1 versus cylinder number 1 on one side, right? So the number of cylinders. So that is your sort of syncing 100 horsepower with 4 cylinders, right? So the 100 horsepower is here, and then our 4 cylinders is here, right? That's what we're working with. So then on the other side of the proportion, you're setting up horsepower over cylinders again. You want to sync up, right? If you've got horsepower on top here, you need to also have it on top here, and then sort of vice versa with cylinders and cylinders. In theory, there's a couple different ways you could set it up. You know, you could also do something where you're saying like horsepower 1 versus horsepower 2, and then you're doing sort of like cylinders 1 versus cylinders 2 on the other side. That would also work technically. I think it's maybe easier to keep track of it if we do it this way. We'll see if I keep doing it that way, hopefully, as we go through these examples. So what do we got? So 100 horsepower for 4 cylinders. So then that would equal sort of X horsepower, right? So this second horsepower value is what I'm trying to solve for. So versus 10 cylinders. How do we solve proportions? Well, the move is across multiply, right? So you're trying to multiply across, in some sense, 10 times 100 and then 4 times horsepower, right? So this is 10 times 100, and this is 4 times horsepower 2 on the other side. So you're cross multiplying to just kind of clean it up. And then from there to obviously sort of get your missing value, you're just doing a quick division by 4, right? Divide the 4 over. On the other side, if I divide 1,000 by 4, I'm going to get 250 horsepower. So that's going to be my horsepower for a 10-cylinder engine. This conceptually makes sense, right? I've sort of increased the number of cylinders, so I'm also going to increase the overall power, the horsepower. Let me look at one from the exercises. I'm going to do another one using proportions. So let's take number 3 here from the exercises. So a cylinder with a bore of 4 inches and a piston stroke of 3 inches has a displacement of 37.7. If the bore remains the same, so the bore is consistent here and the stroke is increased to 4 inches, what is the new displacement? So let me sort of rewrite this information here for us. So skill number 7, question number 3. So cylinder number 1. What did we just say? So the bore is consistent, right? So the bore is 4 inches, but that honestly doesn't matter because that's going to stay the same. So I'm not even going to write it down. What matters here is the stroke, which is 3 inches, and then my displacement, which was 37.7 cubic inches. So then for cylinder number 2, what's happened is I've increased my stroke by an inch, right? From 3 to 4 inches. And the question is, what is my new displacement, right? This is what I'm trying to solve for. So I'm just going to set up a quick proportion, and then we should be able to cross multiply to solve it in no time. So I'm going to set up the 2 values that I know. So I'm going to do stroke 1 over displacement 1 should be equal to stroke 2 over displacement 2. That's the setup I'm going to use. So if I sub these values in, so that's 3 inches versus 37.7, so that should be equal to 4 inches compared to x, right? I'm sort of dropping the units from my calculation. It doesn't particularly matter what the units are here. You could keep them on. I think they're just going to get in the way. As long as we sort of kept everything in the right place, we should be good to go. Cross multiply. So that is, right, 3 times x equals 4 times 37.7. Let's crunch it. 150.8 on the right equals 3x on the left. So then to get my x, right, to get my new displacement, I just need to do a quick division by 3. Pop it in. Divide by 3. So 150.3, 0.2666. We'll call that 50.3, and this is displacement, so that's cubic inches. Conceptually, that makes sense, question mark. It sure does, right? Because what happened is we increased the stroke, right? So we've made this cylinder deeper, so that means our displacement for that cylinder should go up. So that's a direct connection, right? A direct relationship, direct variation between the stroke, aka the height of the cylinder, and the overall displacement for that cylinder. So we'll look at another method here in video number 2. Stay tuned.